this is a magnet. Now see, when I getting deflection in galvanometer means there is a current flowing in this. And the cause of this current may be it has not been connected to any cell or battery. It's only this magnet. So magnet producing electric current. Hello everyone. In this class we will study about electromagnetic induction. See, so far we have studied electricity. We studied magnetism also, but initially these two were considered entirely separate branches. It was only in 1819 that Oersted performed an experiment and found that these two phenomena are related. His experiment was that current carrying wire produces magnetic field. So even the magnetism is produced by current. This is how these two phenomena were linked in this year. After this discovery, now some scientists started thinking just the opposite way. If current carrying wire can produce a magnetic field, then even a magnetic field should be able to produce electric field. And many experiments were performed by many scientists. Two most important are Michael Faraday and Joseph Henry, performed independently, one in US, another one in England. So initial efforts were, two wires were taken, current was there in one wire, so it produces a magnetic field, and efforts were made to produce current in the other wire. But it was Faraday who observed finally and who discovered it finally that a change is necessary. Means the magnetic field produced by one wire should change, only then the current can be produced in the other wire. Now I am giving you very briefly the experiments that he performed. So Faraday's laws. We will talk about two experiments. Experiment 1, experiment 2. First experiment is, there was a coil connected to a galvanometer. So there is no source of current in this circuit. If a magnet is brought closer, if a magnet is moved closer to the coil, a deflection was found in the galvanometer. But it was only when the magnet is moved. Same way, if the magnet is taken away, again there is deflection, but the direction is reversed. If the magnet is kept here and the coil is moved, again there is deflection. If the magnet is moved like this, perpendicularly, even then there is a deflection. But if both of them are moved with same speed in same direction, then there was no deflection. Or when the magnet is kept stationary but close to the coil, again there was no current found in the galvanometer. Experiment 2 was, two coils were involved in it. We have a galvanometer connected to a coil just like this. There is another coil kept close to it. But this was connected to a battery. There was a battery and a key. So the moment K is pressed, there is momentary deflection. So as soon as you press it, there is a deflection in the galvanometer. When we switch it off, again there is deflection. But this deflection is only when we switch on or switch off. When we press the key, there is deflection. When we take it out, when we took it up, again there is deflection in opposite direction. But when we switch it on, deflection, and then it comes at zero. So when the constant current is flowing through this, there is no deflection. Deflection comes only when we switch on or switch off, momentarily. So what is happening in the two cases? Here also, see what is changing for the coil. when the magnet is close to it, the magnetic field lines, it is in the magnetic field, but there is no current. Same way, when the current is flowing through this is behaving like a magnet, but there is no deflection. It means magnetic field itself is not producing any current. But when we move this magnet closer or away, or when we move this, the magnetic field lines passing through this coil, they change. Same things happen here also. So this is producing magnetic field, so I can draw the magnetic field lines. When we switch it on, initially no magnetic field through this, but when we switch it on, magnetic field lines pass through it. Now there is no deflection. When we switch it off, those magnetic field lines again reduce to zero. So when the number of field lines passing through any coil, that number changes, whether it is increased or whether it is decreased, then there is current. What do we call this quantity? This is called magnetic flux, or I can write it in form of vectors, dot product of magnetic field and area vector. So it means now, whenever the flux changes, it means we can change the magnetic field also. We can change the area of the loop also, or we can change simply the angle. So if there is some provision to rotate the coil, a magnet is kept close and then we have a coil and this coil is rotated, again there will be a current in the coil. So whenever a coil is rotated in the magnetic field, there will be a current, because this time theta will change. We can change the area or we can change the amount of the magnetic field. So I can keep an electromagnet. This is an electromagnet actually, right? When we have a coil and current is passing through it. So if I make a provision for changing this current, so if I replace this by an AC source where the current is constantly changing, so there will be a deflection here. If you use proper AC meters, right, there will be a deflection, continuous deflection. So the flux should change. So now, on the basis of these experiments, he gave laws which are called laws of electromagnetic induction. The first one says that the induced EMF is proportional to the rate of change of flux. That constant of proportionality is taken 1 in SI system. So we have minus d phi by dt. We will talk about this minus sign also, which was added later on actually. What is the significance of this negative sign? We will talk about it. So right now, just try to understand that EMF is proportional to d phi by dt is equal to minus d phi by dt, rate at which the flux is changed. So it means if the coil is rotated faster or the magnet is brought closer to the coil but very quickly, then d phi by dt is more, so there will be more current. And if we move it slowly, current will be less. So it depends on the rate at which we are changing the flux. So time is an important factor here. So whenever the magnetic flux associated with a coil changes, an induced EMF is produced. And if we have a closed loop, there will be a current which is called induced current. We can find out the value of induced current also from this. So this will be just divided by resistance. And this EMF, we know how do we write EMF? What is the EMF? It is force per unit charge and then cos theta. So the component of force per unit charge along the loop, E cos theta into dl. This is, or I can write it, E dot dl. For a closed loop, I can write like this. So it is equal to minus d phi by dt. Now from here, one very important thing, E dot dl, closed loop. In electrostatics, this value is 0. So actually, we can conclude that induced EMF, we use the word induced EMF, induced current for this, is non-electrostatic in nature, and it is non-conservative too. It is not conservative, right? Because the value of E dot dl for a closed loop is not 0, it is equal to minus d phi by dt. This is the integral form of Faraday's law of electromagnetic induction. So this current keeps on flowing till there is change in the magnetic flux. Okay, we can write its differential form also, but that is not in your syllabus, but those who want to know. This was the differential form, this is integrated form, del cross E. So now let us see what is the cause for this EMF. Actually, we can describe it in terms of inertia also. We know that we have done the inertia in laws of motion, that all bodies have an inbuilt tendency not to change. So if I explain the induced EMF, taking it inertia only, whenever we are trying to change the flux for a loop, there is opposition to it. If we try to increase the flux, we have in both the cases, whenever we are trying to increase the flux or we are trying to reduce the flux, there is an induced current. And what this induced current is doing? This induced current is trying to decrease it. This is how we find out the direction of the induced current. And there is a rule to find out the direction of induced current also. This was given by Friedrich Lenz, a German physicist he was. In 1834 he gave this law, Lenz's law we call it. Using it we can find out the direction of induced current. And it says, this law says, that direction of induced current is such that it opposes the cause which produces it. Means, the cause of induced EMF is either increased flux or decreased flux. If the flux is increasing, the induced current flows in such a way that it tries to reduce the flux. And if the flux is decreasing, then induced current tries to increase this flux. So it's a sort of inertia. We are increasing the flux, induced current is trying to reduce it. We are reducing the flux, induced current is trying to increase it. So whatever way we do, the induced current opposes it. And this makes it clear why we have used minus sign here. So the direction of induced EMF is such that the current produced by it will always oppose the cause which is producing the induced EMF. This is Lenz's law. Okay, now let us see whether this induced EMF which is produced here is due to some cause already known to us, or was it entirely a different law? Whenever we have current, it means the charges are moving in a definite direction, right? And this is the force. Electric field may apply some force onto a charge, or magnetic field. Now, if I move a coil in a magnetic field, suppose this is the magnetic field, cross means directed inward, and I take a coil and then I move this side, flux will increase, right? Flux will increase. We can find out the direction of current first. Let me check it. If we are taking it towards right, flux is increasing. More magnetic field lines will pass through this ABCD. Now, induced current will flow in such a way that it will try to reduce the flux. How? When the magnetic field due to induced current will be opposite to this magnetic field and the flux will reduce. So this field is inward. Induced current will be such that the field due to that induced current will be opposite to it. So field will be outward. What should be the direction of current in this? Like this or like this, so that the field here is outward. See, I can apply that rule if the current is anti-clockwise, the field will be outward. If the current is clockwise, field will be inward. So it means here it is trying to reduce, so field should be out. So I can take this. This will be the direction. If I move AB towards it, now it will try to increase it. So the current direction will change. Okay, now another thing. AB I am moving towards, right? AB has a number of electrons. All electrons will experience force because they are also moving. When the conductor is moving, these electrons are moving in this direction. So there will be a force. And we can find out that is QVB. So that QVB, the electrons will collect either to A side or side B. We can find out that. Electron is moving in this direction. So it means current. Forefinger, central finger, thumb. Forefinger in the direction of the field, central finger in the direction of current. So it is downward. So it means electrons will experience a force in downward direction. See again. Field inward, right? So this end, if I take rod AB only, this end will become positive and this will be negative. So potential difference starts developing between the two, and two forces are acting now on the electrons. One because of this motion, QVB, and another because of the EMF developed, EE. Okay, so this is same as this. So this is the field which can be written as potential difference upon length. So potential difference is VBL. It means VBL will be the potential difference produced between the two ends, and it is because of the force on charged particles because they are moving in a magnetic field. We call it motional EMF. Okay. Now, so this EMF is VBL. We are moving it perpendicular. If we move it at some angle, it comes out to be VBL sin theta, because then there will be two components of velocity, one along the field, one perpendicular to the field. Along the field will be cos theta, perpendicular sin theta, but here perpendicular components only responsible for changing the flux. Along the field there won't be any change in flux. So VBL sin theta it will become. Anyway, so now a potential difference developed AB, and the reason is the force on the electron because of their motion in the magnetic field. Now let us say we are changing the magnetic field. And magnetic field may be changed even by changing the strength of the magnetic field. Suppose this field is produced by an electromagnet and we connect this electromagnet to a rheostat, we keep on changing the current, that will change the magnetic field produced, and this will change. Now the cause of this EMF can't be the force because of the magnetic field, because the charged particles are at rest. We are not taking the motion due to thermal because that is random, that cancels out. But we are not moving it to one particular direction. Now the rod is at rest, but even now there is an induced EMF because flux is changing. So that cannot be explained. Now the force on the electrons may come either due to this or due to this. Now this is 0, so it means it is coming from this. And it is from here that Faraday concluded that when we change the magnetic flux, whatever be the cause, an electric field is produced. So this time the cause is not. So he gave entirely different and new law. Changes in the magnetic field induces electric field. So E dot dl is minus d phi by dt. This gives us the induced EMF. We can find out now using it. Let us say again I am moving AB towards right with a velocity v, which I took here also. This is L. Okay. Now minus d by dt, and what is phi? Phi is b into a. I can further break it b into a. A is the area of this coil. So if this is x, I'm changing x, that's why I'm writing L x. So it is b, which is not changing, L again not changing, it is only x, dx by dt, which is v. So it is again the same expression. But here I have not taken the cause as the force on the electron. I have taken the cause as just change in flux, whatever be the reason for it. So now whether we are moving the magnet or we are moving the coil or we are just changing the magnetic field, whenever the flux changes, there will be an induced EMF. This is Faraday's laws. Okay. So how to find out direction of induced current? This is quite clear from this example. We can find out using the concept that it always opposes the cause which is producing it. We can take few more examples. This is a coil and I bring a magnet close to it. Let me take, say, north is downward. So there will be induced current because the flux for this coil is changing. There will be an induced EMF and the direction of the induced EMF will be such that it will oppose the increase in the flux. So what will happen? It will repel this because it will also start behaving like a magnet. And how can it oppose this? It will repel this magnet. It means the current will flow in such a way that the upper end of this coil becomes a north pole. So how? This is, I hope you know that, how to find out the poles for current carrying. Clockwise current means south, anti-clockwise north. So this is the weight direction. If I move it up, if I take this magnet up, now again the flux is reducing. It will again oppose it. So again current will flow. But this time it will try to increase it. So it will attract the magnet. So this will become south. So every time the flux changes, there will be an induced current. But for current, yes, the coil should be closed. EMF will always be there whether it is closed or not. But current will be there only when it is closed circuit. So this current flows in such a way that it opposes the change in flux. Okay, this we can explain using the conservation of energy also. How the conservation of energy law is applicable here. Actually, Lenz's law is a statement for confirmation statement for the conservation of energy even in this process. When we are moving it, electrical energy is produced. From where this electrical energy is coming? Energy can neither be created nor be destroyed. It can merely be converted from one form to other. So when we are moving the magnet closer, it starts repelling it. It means now we have to do work against this repulsive force. And energy is spent in pushing the magnet down. And whatever is the work done, mechanical work done, equal amount of electrical energy is produced. So Lenz's law tells us about the conservation of energy also. So electrical energy is coming at the cost of mechanical energy. We are investing work, we are doing work, and equal amount of electrical energy is produced in it. Okay, now in all these cases that we have done so far, there is a well-defined path, there is a rule to find out the direction of induced current, Lenz's law. Now, I will give you examples where induced current are there, but without very well defined paths. Here the current themselves find out the path. This was discovered by Foucault. What he discovered that if we take, I'm giving you an example again, let me say a pair of magnet, and in this region we take a solid metallic plate and we hang it and let us oscillate it. So a north pole, south pole, and I take a metallic plate and hang it like this. Now, what about the flux, magnetic flux associated with this coil? That is again changing. So there will be some induced EMF, there should be some induced current, and yes, the currents are formed on the surface of this. Loops are formed. They are all induced current, and they were named differently eddy currents. Eddies are those circular paths which are formed. So eddy currents themselves basically will decide the path. They very small paths, and then circles are formed, circles for current on the surface. As a result, this gets heated because the current is flowing. One more thing, these induced currents always oppose the cause which is producing it. What does it mean? It means whenever the pendulum is coming inside, the direction of induced current will be such that it will oppose it. And when it is moving out, they will try to attract it. So actually the oscillations of this object, of this plate, no longer remains free oscillations. They are actually damped oscillations. As a result, so if you hang this plate and let it oscillate, count the number of oscillations without the magnets, then you bring the magnets close to it. Then the motion will be damped, and now the number of oscillations will be reduced drastically. We will see that this concept is used in electromagnetic brakes also. So if a metallic plate is moving, we bring magnet close to it, then there will be damping and this will be stopped. And this concept is used, I can give some examples, interesting examples which can be used as project ideas also. If I take a coil, I can put a soft iron core inside it, which increases the magnetic field actually, right? And connect it to a source of current. And let me put a ring, separate ring. Okay, so it's a coil. This one is coil wrapped on this. And insulating it may be a cylinder of cardboard, and then make a coil connected to an AC source, and then put a ring. It may be aluminum ring, iron ring. Now, when the current is passed, so this is now electromagnet. Ring is close to it. Now, induced currents will be produced in the ring, and the nature is such that they always oppose the cause. So, whatever is this, if suppose at any moment this is north pole, so opposite one, it will try to, it will repel it actually. Repel. So this ring will be thrown upward. Actually not just for the ring, I can take it a disc also. So if we have a disc and we put below it an electromagnet and pass current to it, first put the disc on this, and then the moment current starts flowing, there will be induced current in the disc which will oppose them. Oppose means there will be repulsion, so it may be lifted. Then it may come downward due to its weight, and then again up, and then again. Actually, we can float the disc on electromagnet by using appropriate current. This is magnetic levitation actually, and you might have seen in many magic shows. It is shown that a man is in air without the support of any strings or any support from the bottom, just hanging in air. So they use the concept of magnetic levitation. How can we reduce it? Eddy currents. Eddy currents cause heating, so we may reduce them by reducing the area of the surface. So we may make slots in it. Instead of taking one full sheet, we can make various slots. So once area is reduced, the eddy currents will also be reduced. There will be less heating. It depends basically on the application. Sometimes we may need eddy currents, sometimes we may need to avoid the currents. So that's enough for this class.